Certaines personnes m'ont posé des questions sur mon t-shirt, switch to English. People are asking questions about my t-shirt, so I'm gonna, it's kind of an inside joke, so I'm gonna have to give you some background information before I go anywhere. So there's this internet meme that started a number of years ago called "All your days are belong to us," and that sounds like nonsensical English, and it is. It's because it's the bad translation of some horrible Japanese game on the Nintendo whatever. And they sort of badly translated it. And so someone thought that was so funny that they made an entire kind of, film, whatever, devoted to it. So, in fact, there's even audio on this. So this is the intro of this video game. C'est à poste, bon, c'est really
Main screen, turn on. It's you. All right, gentlemen. All your days are belong to us. You're on the way to destruction. What you say? You have no chance. Your life made your time.
Okay, and then this sort of okay, it goes on and on and on and on. Sorry, so it's very funny. So a few years ago, I asked Vladimir Vapnik. I thought there was a nice pun to make, and so I said, I wrote this on a whiteboard. All your days are belong to us. And I wrote his formula on the board, and he doesn't like Bayesians very much. And I asked him, can I take a picture of you? That's the time when I was a director of the lab, he was in my lab. And he was just happy that I was taking his picture. He had no idea what I was, written. And so he stood in front of the board, and I took a nice picture, and his very nice picture of Vapnik is probably the best picture of Vapnik that we have. And I kind of built kind of a joke around this, sort of mean, because sometimes Vapnik looks a bit like a galactic conqueror, so so I sort of made a little picture of him as a galactic conqueror, and and everything, and then it turned out that you go to Wikipedia to the page for Vapnik, and the picture that's linked to it is this one. And so then for some reason I stumbled on a website that sold t-shirts, and it had this t-shirt. And so I wrote to the email on the website, and I told the guy, this is probably where the joke comes from.
It wasn't ThinkGeek, right? Was it ThinkGeek?
It wasn't ThinkGeek, no. It actually has a nice name. I can't remember what the name is, but I can direct you to it later. But so I wrote to the email address, and the guy said, well, I had no idea where it came from, but it was a very funny joke. Turns out the guy is actually a PhD student in machine learning at Carnegie Mellon with Tom Mitchell. And he's sort of producing these t-shirts as kind of a side thing, and so he sent me a few for free.
Great story.
Okay, so much fun. So, all right. So let's go back where we left off. Right, so I was talking about techniques to shape energy surfaces in such a way that the energy is low around data points and high everywhere else. And there is, of course, the full-fledged maximum likelihood, which is most of the time intractable when your energy function is intractable. Second option is something like contrastive divergence, which is used in reciprocal machines and product of experts and other things like that, and field of experts. And another one is score matching, but it's got some problems that it's kind of intractable. I mean, it's very difficult to kind of figure out how to make it work for anything but very simple single layer models. And then there are other things like denoising, contracting autoencoders, and variations of those. And these, so these come out of Joshua Benjo's group. You've already heard about this last year if you were here. And those tend to essentially take a point. So you think of the unsupervised learning system as having a dynamic. And normally the dynamic would be something that would minimize the energy. You start from a state and you try to find a state with low energy. But in the case of denoising and contracting autoencoder, the dynamic is directly learned, and there is no energy function you go through. It's just you directly learn the dynamic, and the dynamic is designed in such a way that if you start from a point of low density, it takes you towards a point of high density, right? So basically, it's instead of a box with an energy and you minimize it, it's a box that directly takes you to areas of high data density. And the way you train this thing is you just train a parameterized function, however you want to parameterize it, from a point in space where you don't have data to a point in space where you do have data. And so the simplest way to do this is you start from a data point, you add noise to it, so it takes you away from it, and then you train your mapping to map from the noisy version to the clean version, right? Simple enough. Contracting autoencoder is a little more difficult to explain. This is the idea that you want this mapping function that reconstructs. You want it to be invariant to changes of the input that are orthogonal to the manifold of data, right? So if you have a manifold of data, let's say this line here, okay, so you have both data points in this line. What you want is you want this point and that point to map to the same place. So in other words, you want the Jacobian of the function in that direction to be 0, right? On the other hand, if you move in that direction, if you move parallel to the manifold, then you want the function to change, because you want a different point on which to map. So that's the idea of contracting autoencoder. You want the function to be contracting across the manifold, but non-contracting along the manifold. Okay, and you can do this with a criterion on the Jacobian that's fairly simple to put together. But here's another one, and that's the one I'm going to concentrate on, and that's the basic idea of sparse coding, but also other types of algorithms like k-means and things like this. You wouldn't think of it this way, but it gives us a sort of reinterpretation of k-means. And it's the fact that what we're going to do is we're going to build our energy function in such a way that it has an internal state, call it a hidden state or a code or a latent variable, whatever you want. And we're going to reconstruct the input from that internal variable. And what we're going to do is that we're going to limit the information content of that code. And by limiting the information content that code can take, we'll have the effect of making sure that the energy is high at places where we don't make it small. It sounds mysterious, but you'll understand in just a minute. Okay, so before I go to this, I want to mention a few things about the basic architecture of a lot of, which you can specialize for a lot of different unsupervised learning algorithms. It's called the encoder-decoder architecture, or auto-encoder architecture. So you have an input variable y, and it goes into a deterministic function, an encoder, and you have sort of a code representation, maybe a feature vector. Think of it as a feature vector z that is supposed to represent y. That goes into a decoder function. And then you have two factors. Think of this as a factor graph with these other variables, and these are the factors, and these are deterministic functions. And the two factors are, one measures the discrepancy between the input variable and the reconstruction from the code, and the other one measures the discrepancy between the prediction of the encoder and the actual latent variable. Okay? And if instead of a term in the energy function here, I just connect this function to that variable and decode, that's just an autoencoder. I have an encoder-decoder, and then the distance function that measures the reconstruction error. Okay? In this thing here, I'm just paying a cost for not making the latent variable equal to the output of the encoder. And it's a very sort of generic architecture. You can formulate a lot of different unsupervised learning algorithms in this form, and I'll come to that in a minute. But before I do this, I want to mention that that includes restricted Boltzmann machines. So restricted Boltzmann machines you can think of as a special case of this sort of encoder-decoder architecture, where the you know, the term in the reconstruction term is kind of a discrepancy or distance between y and the encoding function applied to z. This one is a discrepancy between z and the encoding function applied to y. Okay, and if you define the encoding function as simply a linear function minus w times y, where w is a matrix, and where the distance function is simply the dot product between z and minus wy, then you get this energy function for this term. And then the second term you get the same thing, except it's all transposed, but since w is symmetric, that would be the same. And so the overall energy function is just this plus that, which is simply equal to twice that. And that's just the energy function of the restricted Boltzmann machine. So restricted Boltzmann machines are just energy machines, essentially, of the type that I was talking about, with a symmetric encoding and decoding architecture, where the code is constrained to be binary, at least in the normal version of RBMs. The encoder and the decoder are linear, but because of the constraints of binarity, that makes it sort of nonlinear. And that's pretty much it. Okay, so we're going to build autoencoder architectures like this, but we're going to base them on other principles. Okay, so actually, before I do this, let me go back to RBMs. So in RBMs, they're trained with generally they're trained with contrastive divergence. And so what you have to do is you have to give a data point, run through the system, find the z that minimizes the energy if you want, or find a sample according to the probability distribution defined by this energy function. And for a particular data point, you're going to modify the w parameter to make that energy small. And then you're going to generate another sample by essentially running through the loop with some randomness in it. And you're going to get a second point, and you're going to push up the energy of that point. Okay. And so there is this explicit phase of pushing up the energy of spurious points, essentially in RBMs. But we're going to get around this because that involves sampling, and it's a little unreliable. It's very expensive in high dimension. You have to use, I mean, there are techniques that make it so somewhat efficient, but it's still a little brittle. But here is another idea, and the idea is if we use this encoder-decoder architecture, we're going to start from an input space, and let's say these are points in our input space, and these are corresponding points in our feature space, okay, the z variable. And let's imagine that our training set is these blue points, okay? And let's imagine that my energy function is the reconstruction error. So my energy function is going to be the distance between the point that I started from and the point that I'm going to get back to once I run through the encoder and the decoder, okay? So here the energy function is 0. I start from this point, I go to that point, I reconstruct back perfectly, and energy is 0, perfect reconstruction, okay? Now, if you think about what this machine needs to do, it needs to perfectly reconstruct the data points, and I need to train this machine explicitly in such a way that it does not reconstruct anything else but the data point. So that if I show it one of those points, I don't want it to reconstruct this point. Because if I reconstruct this point perfectly, then that means the energy will be 0, and I won't have my contrast energy function that would be higher on points that are outside of my manifold of data, right? So how am I going to do this? So you can use the trick of denoting autoencoder, which is to say, generate a random point, which is a little bit away from a data point, and then train this random point explicitly to be reconstructed as this clean point. And there the reconstruction error will be large, right? But what we're going to do here is we're going to do something else. We're going to restrict the number of different configurations that the feature vector can take. Okay? So I'm going to tell the system, your feature vector can only take 3 values, not one more. You can place them where you want, but you only have 3. And so I'm going to train now the system to reconstruct those 3 points, and it has no choice but to associate one of those 3 codes to each of these 3 points, right? So it's going to associate this point to that code, and this point to that code, this point to that code. So that whenever you show this point, It goes here, and it gets reconstructed here, goes to this point, goes here, gets reconstructed here. So these guys have 0 reconstruction error. But then these guys have nowhere to go. They're going to have to be mapped to one of those 3 points, right? Because you only have 3. So this guy, for example, is going to be mapped here, but that guy maps back to here, I'm sorry. So the reconstruction error will be large. And so by just restricting the number of configurations in that space, I've automatically forced the energy function to be large on whatever point I have not forced it to be low on, right? So if I push on the energy of these guys, it can't, because it has a limited number of configurations here, it has to make the reconstruction error larger on the points that I haven't trained it on. Okay? So that suggests the idea of sparse autoencoders and variations thereof, and sparse coding as well. Right, so that's the idea here. If you start with a noisy image, it's going to have to map to one of the things that was trained to be associated with a clean one, and so when you reconstruct, it goes to the clean one. So how do we restrict the number of possible configurations in code space? You have several ways of doing this. You can make it discrete, you can make it binary and low dimensional, or low dimensional. You can make it binary, or you can put a prior on the distribution, or you can just put a regularizer on it. Prior and regularizer are just the same thing. One way to do this, for example, is to impose a sparsity penalty, a sparsity regularizer. So, so here's a bit of an example that explains how various unsupervised learning algorithms work, viewed in this sort of energy-based context, if you want. So imagine we have a 2-dimensional input, just x1, x2, and we have a collection of training samples that are distributed along those kind of 3 lines, if you want. Okay. So PCA obviously is an encoder-decoder architecture, right? It projects onto the principal subspace and then reconstructs. So PCA is designed in such a way that the energy function of PCA is going to be 0 along the principal subspace. Okay, the dimension of the space on which where the energy is 0 is the number of dimensions you keep in your principal component. And then as you move away from that subspace, the energy goes quadratically. It's just the quadratic error between the original input and the one that's reconstructed after projection on the principal space, right? So the energy function looks like this. So here, if you train PCA on this, you get a principal component that's kind of roughly like here. And so you get 0 energy here, and then it grows quadratically as you move away from it. It's kind of hard to see here, but you get, the fringes here are white because the energy goes up as you move away. And it's kind of dark in the center. How about k-means? So k-means, so here we're going to do k-means with k equal, so here the PCA is dimension 1. Here we're going to do k-means with k equal 3. So the system has 3 prototypes it can place. And k-means has an energy function which basically is the min of k quadratic balls, right? So the energy of k-means is the square distance between any point and the closest prototype. Okay, so it's kind of hard to see here because of the gamma correction or the lack thereof, but I'm going to try to see if I can change this. I can find the right button. That's a little better. Okay, slightly better. But probably worse for other things. So you can see here, the 3 quadratic balls essentially. Great, thank you. And this is sparse coding, and sparse coding essentially finds low-dimensional subspaces, and the set of low-energy regions is the union of all those low-dimensional subspaces, if you want. And I'll come back to what sparse coding is all about. Actually, that's probably a better example. So here the points are distributed on this spiral. If you do k-means with 20, with k equal 20, you see the centers can distribute themselves around the loop here. PCA finds the principal direction. Sparse coding sort of has this nice little box around the data points, and ignore this for now. So how are we going to use this to do deep learning or unsupervised feature learning? And I think I'm going to revert to the original configuration, which I think was sharper. There we go. So we're gonna use sparse coding, and so sparse coding is a decoder only. The original version of it, which is Ossazenfield 1997, is a sort of decoder only graph. So it doesn't have the encoder part, but I'll introduce one later. So you start from an input, let's say a patch from an image, call it y, and z is going to be a feature vector. And the energy function is going to be of this form, so it's the square distance between the y vector and a linear matrix applied to the z vector, the feature vector. So it's kind of a generative model. It goes from the feature to the input, and not the other way around. It's not a feed-forward model, it's a feedback model. And then there's a regularization term, which is just the L1 norm of z, the sum of the absolute value of the components of z, which ensures that z is sparse, as lots of zeros in it, right? So that's the energy function as a function of y and z. If I give you a data point yi, what you have to do is find the value of z that minimizes this, and that's the inference process, okay? So inference consists in finding the z that minimizes the energy for a given y. It's this process. And then learning consists in minimizing the average energy for the optimal z over a training set, okay? So the process for training is you take a particular y data point, you find the z that minimizes the energy function, and then you compute the derivative of the energy function with respect to wd, and you update wd so as to make it smaller, and then you go to the next point, okay? And there's one slight trick you have to apply, which is that it's actually ill-determined because you can sort of multiply z by 1/2 and multiply wd by 2 and you get the same result. And so you have to normalize the columns of wd, okay? And so that runs wd in such a way that all the data points that you have are optimally reconstructed by a linear operator applied to this sparse vector. Okay, so the sparse coding and sparse modeling. So sparse modeling is the learning part. The problem with that is that it's a slow inference process. So once you've trained the WD, if I give you a y, you still have to minimize this L1, L2 function to find the z that encodes a particular input. And if you do this for every patch in the image, it's going to cost you quite a bit. So you don't want to be doing this. At least not for real-time kind of thing. And again, you could think of this as kind of a decoder-only sort of generative type model factor graph. So here, inferring y from z is easy, but inferring z from y is hard. So the idea we had a few years ago, the paper of which was rejected from all major conferences, is to introduce a feed-forward encoder, and we're going to train this encoder to give us an approximation of the optimal z for all the y in your data set. Okay? So first we're going to, so we can do this in two phases. First we can train the decoder so that y's are reconstructed from sparse z's, and the decoder now is trained. Now we run our training set through this system, and for each y we generate the corresponding optimal z. And now we have a bunch of training pairs, y and optimal z. And we can train a feed-forward predictor to predict the optimal z for a given y. Okay? Now that sounds like a free lunch, or that sounds like it couldn't possibly work because the result of the process of computing the optimal z for a given y here is very complicated. It involves minimizing this L1 L2 function, and it's not trivial. It's iterative and blah blah blah. So how can we possibly hope to be able to do a good job at predicting Z with a simple encoder? Let's say an encoder that's say, a linear operation followed by a very simple nonlinear operation. But the point is, we're not trying to do a good job at predicting Z everywhere in the space. We're only trying to do this on the data point that we are interested in. Okay? At other places, we don't care. So, so there is a hope, perhaps, that on this kind of small subspace of natural data that we're training the system on, perhaps we can actually do a good job at predicting the optimal Z without breaking any law of the universe. Right? So that's called predictive sparse decomposition or predictive sparse coding. And again, it's an archive paper from actually 2008, but we only posted this on archive in 2010. We had it as a tech report before that. And then the follow-up papers were accepted before this one ever got published, so we never published it. And the energy function really has three terms. We do this whole thing simultaneously. So one is the reconstruction error, and the other one is this prediction error. The difference between the code vector and the output of the predictor, and then the sparsity constraint. And the form that we give to this G function usually is very simple. It's something like take your Y vector, apply some sort of matrix to it. The dimension of this matrix is the same as the transpose of WD. And then apply a component-wise shrinkage function, where a shrinkage function is something like this, something that sort of shrinks every value towards 0. Okay. So if you train PSD on MNIST, what you get as the columns of WD or the rows of WE, which actually are pretty much the same, is you get those kind of filters. So if there are the columns of WD, you think of them as basis functions. If there are the rows of WE, you think of them as filters, right? But really, they play the same role, and they're usually pretty much the same. And so those look like little parts of characters, little strokes. And what that tells you is that you can reconstruct any digit as a linear combination of a small subset of these guys. That's what the sparse coding gives you, right? And so the best thing the system can do is come up with the idea of stroke, because that's the best way of decomposing the character into elementary parts. This is the learning algorithm running and learning those filters when it's trained on natural image patches. So you start from random initial conditions, and pretty soon you start to see those sort of oriented edge detectors, kind of V1-like oriented edge detectors. And you know, the number of iterations is actually quite small, and if you think of this in terms of sort of biology or whatever, this would literally take minutes. So if you're a small animal and you run this algorithm, within minutes of being born, you have edge detectors. And now if you are a evolutionary biologist or neuroscientist, and you try to figure out if those things are determined by the genome or trained, you have to be really fast, because after the first 5 minutes, basically, you can't tell the difference. So this idea of using a predictor to predict the result of a complex algorithm on a subset of the entire set is actually fairly general. And my former postdoc, Carol Greger, had the idea of actually making the encoder slightly more sophisticated and have it mimic the structure of the algorithm that we would run if we wanted to actually solve the sparse coding problem. So it turns out there is and this idea has been picked up recently at SCML by Bronstein and Guillermo Sapiro and a student. And the idea is, so if you want to solve the sparse coding problem, so I give you a Y, find me the Z that minimizes the sum of the reconstruction error and sparsity. There's a simple algorithm called the iterative shrinkage and thresholding algorithm, ISTA. And there's a fast version of it called FISTA, okay? Fast iterative shrinkage and thresholding algorithm. And it's an iterative algorithm of this type. You start with Z of t equals 0, and then you compute, you multiply Z of t by the dictionary matrix, and then by the transpose of the dictionary matrix, and then you subtract the Y before you multiply by transpose of the dictionary matrix, multiply this by some constant, and then subtract this from the z you had before, and apply a shrinkage function, component by component. This basically shrinks everything to a 0, where the threshold, the shrinkage parameter is lambda over L. And then you iterate this, and if you wait long enough, z of t converges to the solution of the sparse-Levi problem, to the optimal z for the y. Okay. So what we're going to do is we're going to rewrite this like that. Okay. So this matrix here we call S, and we're going to have another matrix here, WEY, which is this like WD transpose Y. You said WD transpose I, we have WE. And S is kind of like the identity minus 1 over L, WD transpose W. But we're going to allow S and WE to be the trainable parameters of our encoder. Okay. So our encoder is going to look like this, basically. We take Y, apply WE, and then shrink the components, then apply this S matrix, then add it to the previous product of E by WE, shrink again, and then iterate this. Okay. And if we set S and WE to the right values, then this actually will produce the best optimal code for Z. But what we're going to do is we're not going to do this. We're going to run WE and S in such a way that this module here gives us the best possible approximation in a given number of iterations. So we're going to say we can afford to run this for 2 or 3 iterations. Give me the WE and S that will give me the best approximation of the optimal code in 3 iterations of this. Okay. And you can think of this as a kind of a recurrent neural net, which you can unfold. So this is an unfolded version of this for 2 iterations. And you just train this with backprop. And what you get is that, so these are kind of reconstruction errors or energy as the y-axis. This is number of iterations. So this is the ISTA or FISTA algorithm. And this is this trainable ISTA algorithm. And you see that the reconstruction error gets low much faster than with the normal algorithm on the data that we train it on. Of course, not on the entire space. We call this LISTA for learning iterative shrinkage and thresholding algorithm. And so these guys, Bornstein and Stefiro, have applied the same idea to all kinds of other stuff, like blind source separation and things like this. And they have sort of real-time blind source separation demos running on iPads, and it's pretty cool. Okay, so we're going to use this to pre-train the filters of a convolutional net in an unsupervised manner. Okay, and so this seems a little circuitous, but essentially, if I go back to the PSD algorithm, the PSD architecture, you could think of this as an image patch that's seen by a filter bank of a convolutional net. You can think of WE as the filters. You can think of G as the nonlinearity that comes after the filter. And you can think of this as the pooling operation, although that's not really clear. But you can think of this entire path here as being kind of one stage of a convolutional net, if you want. Okay? So we're going to use this unsupervised learning to pre-train the filters of this convolutional net to do a good job at extracting features from which we can reconstruct the input, so that we know no information is lost. And then we're going to get rid of the feedback and use this. So as I said before, the basic architecture of a single stage of a convolutional net is this subtractive and divisive contrast normalization. I'll say a few words about this. The filters, convolutions, the shrinkage operator, and then a pooling operation, which now the more recent incarnations we use L2 pooling. So the contrast normalization consists in essentially taking all the feature maps at one particular layer and normalizing every value within the feature map by dividing every value within the feature map by the standard deviation measured over all of its neighbors over features and over space. That's the divisive one. And we apply this after having applied the subtractive one, which consists in essentially subtracting, replacing every value by itself minus the weighted average of its neighbors over space and features. Okay, so it's a poor man's whitening, if you want, decorrelation, local decorrelation. Okay, so here is how we use this unsupervised learning algorithm to pre-train convolutional nets. We take an image patch, we take a bunch of image patches, we train our little autoencoder, sparse autoencoder on this, and once we're happy with it, we get rid of the feedback part, we just keep the feed forward. And we can wrap a pooling function inside of this. I'll tell you about this later. Then we we run this through all of our training set, generate some first layer features, stick another autoencoder on top of this, train that unsupervised. Once we're happy with it, get rid of the feedback and just use the feed-forward encoder as a feature extraction. And then stick a classifier on top. And then what we can do is we can train the classifier supervised, or we can backpropagate through the entire thing and refine, fine-tune the entire thing with backprop. Because it's just a convolutional net by now. So if you apply this to natural images, like Caltech images or whatever, these are the typical filters you get for the first layer. These are the filters for second layer, second stage. And you get sort of decent performance on Caltech 101. Nothing to break any records, but these are results from 4 years ago. But you get results that are on the same order of magnitude as what you get with SIFT and k-means vector quantization. It's not as good as if you use sparse coding at the second stage, even though this is using sparse coding. But it's simply because the networks that we've trained using this scheme are much smaller than the ones that we've trained or other people have trained with SIFT features. One thing that seems essential though, so I'd like you to look at this particular row here. So this is a purely supervised convolutional net. And the different columns correspond to different types of architectures. So this one is a convolutional net of the type that we used in the early 90s and late 80s, which has sigmoid nonlinearities and average pooling and things like this. And this one gets 30% correct on Caltech 101, which is really horrible. And the difference with this one is that this one uses the contrast normalization and also uses a different type of nonlinearity. So instead of a sigmoid function, it's a rectified sigmoid function. It's the absolute value of a hyperbolic tangent, if you want. Okay. And this makes the performance just much better. The difference between those two lines is that this one uses unsupervised pre-training and this one uses purely supervised training. There's a bit of a difference, but not much.
Still average pooling or max pooling?
So PA means average, PM means max.
Okay.
So if you use max pooling, the utility of the absolute value rectification is not as big, because max basically does rectification. Eventually we got this up to 72% or so, but that's not very interesting. So here's an interesting thing, which is we can do experiments kind of similar to, I guess, what Marcel was talking about, which is trying to figure out the sort of optimal stimulus that would maximally activate a particular feature. Right? Okay, so I forgot to mention something, which is that we get surprisingly good results with completely random filter. There's no training whatsoever here. Okay, so if we don't have the right nonlinearity and we just use random filters, we just train the classifier. The results are terrible if we use the classical type convolutional net, but if we introduce those rectification and contrast normalization, we get results that are surprisingly good. I mean, they're really close to these actually. And that kind of puzzled us quite a bit. It actually got, depressed some of my students. But it's kind of interesting. There's some sort of magic going on with the contrast normalization that makes the performance go up by a factor of 2 with random filters. So that seems to be really, really important for good performance. Now it turns out that this result, that random filters work almost as well as trained filters, is only true for Caltech 101. Everything else we tried on, learning filters really makes a huge difference. I'll show you some examples later. But it puzzled us a bit enough that we tried to figure out what the story was with these random filters. And so here's a bunch of random filters, first stage random filters, and then they go through the pooling operation, and we asked the question, what input stimulus will maximally activate a particular complex cell after pooling that looks at a particular output filter. And what you see is oriented grading. It's very strange. Now, this is the same thing with learn filters, and those learn filters are oriented, are direction sensitive. And so it seems logical that the pattern that would maximally activate this this filter would be a grating of the same orientation because of the the pooling on top of it. And that's what you observe. But even for filters that are essentially random, you still get those oriented gratings mostly. And it's because the contrast normalization essentially magnifies the the difference, the anisotropy in the filters, and it makes them more orientation selective. So it's kind of cool because that means if you are evolution, that means you can give vision to simple animals without having figured out how to do learning yet, as long as you figure out contrast normalization. Right, so here's the thing that shows that this is really only true for Caltech 101. So this is another training set called the norm data set, very different from Caltech. In this one we have way more labeled samples. And so the Caltech 101 regime is here, where we have 30 training samples per category. But if you have 500 or 1,000 training samples per category, then learning the filters actually helps a lot. So this is the error rate as you increase the number of label samples, where the filters are random, they don't learn, you just run the classifier. This is where the filters are purely unsupervised, and this is where the filters are trained either completely supervised or with a combination of supervised and unsupervised. And this is without normalization. So normalization seems magical. It's magical in the sort of low data regime, but if you have lots of data, it's not that useful. Excuse me.
Here, it's only 2 stages, so you have also experiment with more stages?
It's only 2 stages here. Yeah. It's hard to actually get better results with 3 stages for this kind of problem. But there is a problem with sparse coding, which is that it produces very redundant code. And the reason is it's trained at the patch level. So you show a 9x9 patch, and you ask the system to learn basis functions that reconstruct a 9x9 patch. And what the system has to do is that it has to produce translated version of the same filter at various locations to be able to reconstruct an edge wherever it appears. It's kind of stupid because you're going to apply those filters convolutionally. So, this guy, this guy, and this guy, and this guy, and this guy, what you are going to produce exactly the same output, just so you shift it from each other. It's incredibly redundant. So, one idea that we had, and we worked on this simultaneously with a colleague at NYU, Rob Fergus, who kind of had a different idea of how to use this, is to use convolutional sparse coding. So sparse coding, you can think of it this way: the energy is the square distance between the input vector and the sum over columns of WK, the sum over basis functions, of one column of the one basis functions multiplied by the corresponding coefficient. So this is a scalar, this is a vector, and the weighted sum here is the reconstruction. We're just going to do the same thing, except that the sum here is going to be over the application of a convolution kernel convolved with a feature map. Okay, so now zk here is not a scalar anymore, it's an image. wk is not a vector anymore, it's a convolution kernel. Okay, and we take one zk, we convolve it with the wk. We do this with multiple zks and with multiple wks, sum them up, and that's our reconstruction. Okay. And now the system learns that if it needs to place an edge at a particular location, it doesn't need to. First of all, it needs to only have one horizontal edge filter. It doesn't need to have it at multiple locations. And second, it's going to make those maps really sparse. So these are the filters we get when we train with this convolutional sparse coding or PSD. And these are the filters that we got with the patch-based version. So the patch-based version, the system basically spends all of its resources learning shifted versions of the same filters. Whereas here, since it doesn't need to have that, it already has them because of the convolution, it can learn new filters that wouldn't otherwise pop up. So it has, center surround, it has crosses, it has endpoint detectors, it has gratings, it has another endpoint detector, it's got corners someplace here. It's got another corner here, cross detectors and things like this. much more diverse. It doesn't make a huge difference in terms of performance on the small number of data sets that we tried, but it does on at least one application, which is pedestrian detection.
Can you explain why you don't have such improvement?
You know, Architect 101, it doesn't, but nothing does, because it's just so overtrained, so small, and blah, blah, blah. But pedestrian detection makes a difference. So, actually, let me show you a video. So this is a pedestrian detector. So basically, it's just a convolutional net trained to either turn on or turn off. If there, turn on if there is a pedestrian centered in its field of view, and turn off if there isn't. And then you apply it to the entire image, and then do some non-maximum suppression. And then you draw little boxes around the detection where the intensity of the box, the intensity of the blue color depends on the score, essentially. So you get a lot of false positives, but they're essentially below threshold, like here, they're pretty faint. And it pretty much detects everybody. A few false positives here. So that works quite well. It's an endless video. In fact, for pedestrian detection, so this is a test on the Invariant dataset where a lot of people have tried lots of techniques on it. And the axes here are the number of false positives per image. So this line here is 1 false positive per image. And then what you measure is the miss rate. So how many pedestrians do you miss, or what percentage do you miss? And so the better systems are kind of down the bottom here. Of course, there aren't any. The best system is this one, and that's our system. And these are, latent SVM, payload first and swap, blah, 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 hog and whatever. And we need them all. There's a difference between the performance of the system with unsupervised pre-training and without. We also tried this on a whole bunch of different data sets, and we pretty much come out on top of almost all of them. This is the Daimler set. So this is all trained on the INRIA data set, but tested on various other test sets. And these are for fairly large pedestrians. So again, a whole bunch of different systems. Our system is this blue line here. Here. ETH, INRIA, Brussels. These are for slightly smaller pedestrians, and our system is really not trained for small ones, but we test like everybody else. So here we're not the best on the Brussels, but pretty much the best on everything else. And the cool thing with those unsupervised running algorithms and feature learning is that we can apply the architecture to just about anything that comes to you in the form of arrays. So we've applied this to musical genre recognition. So there is this GTZan dataset, 1,000 clips of music, 30 seconds each, from 10 different genres, blues, classical, country, blah, blah, blah. And what we do is we trained those PSD features with 512 filters. The input representation is called this constant Q transform. So it's sort of a filter bank where the frequencies are spaced geometrically so that you have a constant number of filter bands per octave. In our case, 24. And so basically 2 per half tone. And we get, so this is the kind of representation you get with contrast normalization, filter, shrinkage, mass pooling. In your classification, we didn't try with 2 stages, but we think it would work better. And the nice thing is that the features you get when you look at the basis functions, they basically come up with chords. They've discovered chords. Things like minor third, perfect fourth, perfect fifth, etc. And the performance we get is with this thing is a little below 84%. The best results that we know in this data set is a little above 84%, and there are 2 results in 92%, but I'm told by the experts in the field that there's a sort of major methodological problem with those results, that basically training on the test set or whatever. So nobody believes those. In fact, there are papers that say it's invalid. Okay, so the other set of experiments, I'm going to go very quick through this, that we did was to, oh, before we do this, let me show you a little demo. So I have a webcam here, and you're not seeing what I'm seeing yet. And I'm running a convolutional net on this on the contrast normalized image at the bottom here, and I'm extracting feature vectors of size 256, and I'm extracting them over 9 windows over this input. And I didn't connect. So this system was trained and supervised, and then trained with supervised refinement on Caltech 101. Not such a great training set. What I'm going to do is I'm going to train it using. I'm going to stick a nearest neighbor classifier on top. Actually, a parts of window classifier, but it's pretty much nearest neighbor. And I can train it with one shot to recognize objects, whatever they are. So let's say we have a box of candies. Candies. These are candies. Okay, so I'm going to hit the C key for candies. Okay, I've hit the key 3 times, which is indicated in the square brackets, which means I have 3 prototypes or 3 templates for 256 dimensional templates for the candies. So if I point the camera someplace else, it doesn't say it's a candy. And those are what? I'm going to call that Wi-Fi. Oh, I hit S. Sorry, I meant to hit W. That's okay. We call that S. So S, C, and then what? We have here. That's a bottle. Where's the B? So that's B. Okay, so we have a bottle. We have candies and the S stuff. And I don't know what else we can have. Well, the face. F. Okay, so the face. It's a bottle. It does kind of a gestalt, so it's not just the bottle, it's just everything, you know, around the bottle. The candies, the cards, you know, the plant.
You should change the lights if you
Change the
rotate the
light?
camera.
Okay, so I can move the camera, we'll see. So first of all, let me try another bottle, maybe it will even, does this work? It's not really not sure about this. So I can certainly rotate the camera. Okay, so we have candies here. Still candies. Lost the candies. Back to the candies. Change the size perhaps. Just be robust to size. There's no multi-scale processing, it's just looking at this image, you know, no scale. It's just a pooling operation that sort of makes it size invariant. The cards. That's pretty robust to rotation for some reason. I guess the face isn't slightly. Well, you rotate the same direction I rotate. So. Yeah, that's pretty robust. So you get the idea. And then, you know, you can use this for, say, robot localization. So let's say you guys are, well, that's a face, yeah, indeed, but I need to erase that. So you are number 1, number 2, number 3, 4, 5, All right, so now I'm going to move back. So you're 7, I'm going to move the camera back. 6, 5, 4, 3, 2, 1. And I'm not sure what the back quote is. That probably hit the wrong key in the wrong path. So, you know, it's pretty, the features are pretty robust. I mean, they've only been trained and supervised with this sparse coding, and then refined supervised on CATREC 101. But then I'm using them as, you know, features for nearest neighbor classifier. So my student Ilan Moreau did some fairly systematic experiment on sort of more traditional computer vision pipeline with, you know, SID features here and kind of sparse coding here of the type that I guess Stefan talked about yesterday. Sebastian. And the bottom line is that sparse coding works better than everything else. At least better than humans. So the last couple of things I wanted to talk about was how you can learn not just features, but invariant features, or locally invariant features, or robust features. And we're going to do this through group sparsity. So we're going to modify the energy function for the sparse autoencoder in such a way that instead of computing the L1 norm of the Z vector, we're going to compute the sum of the L2 norm over groups of features, right? So we take a bunch of components of Z, we call this a pool, Pj, and then for all the Ks that are within this pool, we compute the sum of the square of the components of that, then compute the square root, and then sum that up over all pools, right? So a pool is like a complex cell. It takes the activations of the components of Z within the pool, and it computes the square root of sum of square of these guys, L2 norm, L2 pooling. We call this L2 pooling. And what does that do for us? So when we train this autoencoder under this kind of weird group sparsity constraint, what it drives the system to do is that it wants the minimum number of pools to be on at any one time, right? Because sparsity, the energy criterion is the sum of the activities of the pools. So it wants the smallest number of pools to be active at any one time. But within the pool, it can have as many units within the pool active as it wants, because it's an L2 penalty. And so that causes filters that fire together to group themselves into pools, right? So if you have two filters that detect very similar features, perhaps edges at very similar orientations, they tend to be activated together. And so if the system wants to minimize the number of pools that are on, it's going to put those two filters in the same pool, right? There's a long history of people doing this in various contexts, starting with Cardozo at NST and Hierarchies and Euler in the early 2000s. So they weren't doing sparse coding, they were interested in multidimensional ICA, and they called it subspace ICA. Well, Cardozo calls it multidimensional ICA, and Hierarchies calls this subspace ICA. So this is a decoder-only kind of thing for multidim ICA, and subspace ICA is encoder-only. The sort of similar idea that came out of Jeff Hinton's lab about 10 years ago with the product of experts, where also we had some sort of pooled, L2 pooled, encoder-only kind of system. We came up with this idea of group sparsity a few years ago, using this PSD idea with L2 pooling. And there were sort of other people doing group sparsity around the same time, maybe slightly later in Jean Ponce's lab at Normal Sud, at INRIA. This is Rodolphe Genaton and Francis Bach and Jean Ponce. And then sort of independently of this, Kwok Lee at Stanford, who's a student of Andrew Ng, came up with something called reconstruction ICA, which is sort of a square autoencoder kind of thing. But he tied the encoder and decoder weights, kind of like an RBM. And then more recently, he had the idea of decoupling the encoder-decoder, and that basically comes down to exactly the same algorithm that Carol Greger and I and Koray Kavucholu with Invariant PSD came up with a few years later. this is the technique that's used in the paper that some of you may have heard of, that was published at STML, and that got, made the front page of the New York Times, where, people and cats and whatever. So they use an unsupervised learning algorithm, they call, and this recap thing, but it's actually exactly equivalent to this. Except the encoder is linear, which is a mistake. So here's how it works. So here what we've done is that we trained a whole bunch of basis functions using the PSD. And the groups are sort of square blocks of filters. And this arrangement here, this two-dimensional arrangement, is arbitrary. It has nothing to do with the topology of the image. We just take all our filters and we arrange them on a 2D topology. It's actually toric. So the top touches the bottom, and it's a donut. And what happens is that the filters that are similar tend to group themselves together, and you get those nice topographic maps of smoothly varying filters as you move around, and you get those sort of pinwheel patterns. And those are things you observe in the visual cortex. You see things like this in the visual cortex. The oriented edge detectors organize themselves in patterns very much like this.
So, sorry, I don't understand. How do they group themselves?
Well, so one of the square is one of those pools. Okay, so you compute the sum of the square root of the sum of the square of the coefficient attached to each of those filters. Okay, and those groups, you have many groups like that, and they overlap. And so by doing the sparsity penalty, by trying to minimize the sparsity penalty, the system wants the minimum number of groups to be turned on at any one time. And the only way you can do this is by grouping together within the single pool, if possible, all the filters that will turn on simultaneously. And generally, filters that turn on simultaneously tend to be similar, right? So you get pools of similar filters, and you can think of the activity of a pool, the square root of some of the square of the activities within the pool, as being a complex cell, essentially.
So do you have any ideas on choosing the optimal distribution of pool sizes?
No, we haven't really experimented with this very much. No.
So it's during learning that they organize?
That they organize themselves like that, yes.
Okay.
So this is the same thing, except here those are retinotopic. So we take an image, 100 by 100 pixels or so, and we have a 4-time over complete set of filters. So little groups of 4 filters here look at the same place. They have the same receptive field, local receptive field. I think it's 9 by 9, and then they're shifted by 1 pixel as you move along this. And you train the system, and it organizes itself in those pinwheel patterns. And that's very much like what you observe in the primary visual cortex. You can find those kind of single points and encode you can fit Gabor filters to the filters to figure out the orientation, and then do a color encoding of the orientation. And you get those kind of encoding of directional sensitivity, which are very similar to what you find in the neuroscience literature. Yeah, this is just a plug for Stefan Malaz's work, but many of you probably heard about this maybe last year or 2 years ago, I'm not sure. So I think it's very interesting work that sort of gives some theoretical underpinning to a lot of the architectures that I've been talking about. I think it's really cool. So it's free advertising. So more recently we came up with a different idea for doing sparse coding, which is based on sort of a funny quadratic term, which you can think of as lateral inhibition. And the idea is the following. What you want is, you have this regularization term, which is, so this is a vector, and the notation here is indicates the fact that this is a vector formed by whose components are the absolute values of the components of Z, right? So take the absolute values of each of the components, you get a new vector, and call this Z bar. It's not a modulus, it's actually a vector that you get here. And then you're going to compute some sort of quadratic form, Z transpose SZ, with this S matrix. And S matrix is a mutual exclusion matrix. So to minimize this energy function, you want to reconstruct the input as a filter basis functions applied to a feature vector. But then the feature vector wants to minimize this. And if you have one term Sij that's non-zero, the best way to minimize this term is to make either Zi 0 or Zj 0, right? If Sij is non-zero, then either make Zi 0 or Zj 0. It's like mutual inhibition. So what's the advantage of this relative to normal sparse coding? The advantage of this is that you can put some structure in S. You can decide a priori that some terms in S are going to be 0 and some terms in S are going to be non-zero. And that allows you to put some structure in the organization of the pools, if you want, which is more direct than with the group sparsity. And the slight problem with it is, of course, now the function is non-convex anymore. It used to be convex before with L1, but this is very highly non-convex as a function of Z. And so a lot of theory breaks down. But it's more kind of biologically plausible, perhaps. So here's an example of results where here the filters have been organized in a tree. And so the tree is such that the term in the S matrix that exists between two filters or two basis functions is a function of tree distance. So this guy and this guy have 0 on their S term, okay? Because one is parent of each other. So if a filter is a parent of another, then the S term, corresponding S term is 0. So along the tree, the S terms are 0. But then the S term between pairs of filters depends on their tree distance. And what you see is that the filters kind of organize themselves from low frequency to high frequency as you move from the center to the periphery. And then there's more or less a smoothly varying orientation selectivity when you go around the circle here. And here you get kind of complementary pairs or quadrature pairs, depending on. You can also get those kind of 2D topology, continuously varying feature maps. Actually, I'm going to skip this and not talk about that. And I'm just going to show you, for those of you who haven't seen this before, I'm just going to show you a video, a couple more videos.
Can you apply the last words for scene categorizations with these lateral animations?
Pardon?
Did you apply these last works for any?
No.
Yeah.
There's a lot of things going on in parallel, and we have to kind of.
Very interesting.
Yeah, exactly. Okay, I think that's this, yes. So this is a project that I did about 3-4 years ago, a robotics project, where the goal was to train a robot to drive itself through nature solely through vision. And we used one of those convolutional nets to do this, and we used this unsupervised pre-training using autoencoder, although an early version of it. So the robot has 2 stereo camera pairs, GPS, onboard computers, and an IMU, and real encoders. And here, it's using a purely classical stereo vision algorithm to do sort of 3D map of the environment and avoid the obstacles by figuring out what sticks out of the ground, essentially. And here we just turned on a long-range vision system, which is monocular, and uses a convolutional net to essentially label every pixel in the image as to whether it's traversable or not. So it's very much like the scene parsing algorithm, except there's only 3 categories, essentially. Traversable, not traversable, or the kind of boundary between 2 things. Let me go back a little bit here. And so here it sees from the start that there's a row of people, and it goes around. And Marco here is holding a radio transmitter, but is not actually driving the robot, is holding the kill switch. And so what we do is we figure out the ground plane that we are sitting on, and we extract bands from the image that are contrast normalized. And their height is also normalized in sort of inverse distance, if you want, so that objects appear always the same size independently of the distance. And then we apply a convolutional net to it. And so the cool thing about this is that we don't have to supervise the system. It supervises itself. And so we get an input image, we compute stereo labels. Using stereo vision, we can figure out if something is on the ground, or if it's flat, or if it sticks out. And so we use this to train the convolutional net on the fly as the robot runs to train itself to distinguish between traversable areas and non-traversable areas. Okay, so it's kind of self-training. It's actually called near-to-far learning, because you use your knowledge of whether something nearby is an obstacle using a particular sensor, stereo vision in this case, to train a long-range system that does not have access to this sensor. The reason you want to do this is because stereo vision only works up to 10, 12 meters or so. Beyond 12 meters, you can't tell, there's not enough disparity to tell if something sticks out of the ground or not. So you use these, so you take, you could think of, applying the convolutional net to this, and then you get labels, and you train it just like the scene parser, essentially. So like a dense labeling. And then you apply the convolutional net to the whole image, and it tells you, well, there is a little passageway here that you couldn't see in stereo, and so you're going to be able to drive through it. And it works really well. It labels the path here all the way through. It says you have to go around this building, and then it says there's a road here you can't go through. And that all runs in real time on this sort of 7-year-old computer in the belly of the robot. Right. So there's actually 3 vision systems in the robot. There's the kind of stereo vision system that I showed you about, that I told you about, based on stereo first and then on the long-range convolutional net. And this one runs at about 1 or 2 frames per second. But that's too slow to sort of quickly react to obstacles you didn't expect. And so there's another short-range, low-resolution, fast frame rate, stereo-based vision systems to do short-range obstacle avoidance. And this one runs at 7 to 8 frames per second. And once you've labeled the images of all those things, you can put this in a map, and then within the map you can do planning to go to a particular goal. And the map is so-called hyperbolic polar map, which is centered on the robot. So it's a bit like what I guess you were showing. And there is the same idea I think you were mentioning of kind of accumulating evidence in the map for what is traversable and what isn't traversable. So the map is sort of integrated over time, integrates information over time as to where obstacles are. To make this work properly, you have to have some sort of visual odometry. You have to be able to know which way you're pointing within the map. And that's what this explains, but I'm going to skip that. And then there is some learning also taking place in the controller system, where the planning of the short-range trajectory is done using kind of a catalog of possible trajectories that have been learned by running the robot lots of times in sort of multiple configurations, and then picking the possible trajectory that we know we can follow because it's been done before from the current speeds of the 2 wheels, so as to avoid obstacles. So this is an example of this, where we turned off the long-range vision system. We crippled the vision system so we can only see up to about 2.5 meters in front. So it has to react quickly. This is accelerated twice, so it's twice the normal speed here. And then Pierre can jump in front of it and not get killed. So these are Pierre Samanet and Raya Hetzel. And Pierre is still a student with me. Raya graduated. They're pretty confident that they're not going to be run over by this robot. And they can be confident because they actually wrote the code. And that's it. Thank you very much.